Welcome ENET 130 at Bellingham Technical College. This is our semiconductors portion of our electronics studies, and this is the last of three in our lectures about basic diode characteristics. So to date, in our first lecture, in our chapter 1 of our James Fiore textbook, we discussed semiconductor materials, what makes them semiconductors, energy bands, hole and electron charge carriers. We defined the p-n junction as an area, a physical area where p-type and n-type semiconducting materials meet, and the majority charge carriers from both annihilate, and we get a little layer of intrinsic semiconducting material that forms an energy hill that we have to overcome with an applied voltage to get the semiconductor junction to conduct, and that it only conducts in one direction. So we formed a diode, or a one-way conductor. We looked at characteristics of diodes, how to read a spec, and then we looked at models for diodes in a circuit in terms of a switch that was open if the diode was in reverse bias, closed if it was in forward bias, and then included an opposing voltage to represent the magnitude of that energy hill. We acknowledge that diodes, like any other material, has some ohmic resistance, and we looked at how we would define that ohmic resistance on our exponential current versus voltage curve that represents how diodes work. And the most important takeaway there was the diode ohmic resistance changes depending on where we're operating the diode, how much current we're forcing through it. And then we used our circuit model to analyze some simple circuits with diodes and reinforce the need to use Kirchhoff's voltage law and our basic definitions of series and parallel. So we now have a good grip on how to use a standard switching or rectifying diode in a circuit. So now in our last lecture, we're going to look at other types of diodes. And the first thing I'm going to do before we dive into how these are different is I'm going to tell you how they're all the same. With the exception of a Schottky diode, every one of these has a p-n junction. There may be different materials. The nature of that junction may be different. The way the device is manufactured and calibrated may be different. And even in the case of the Schottky diode, it doesn't have a p-n junction, but it has a different type of junction that functions the same way. So we're going to have an energy hill, and we're going to have different types of charge carriers in all of these. So all of our basic concepts of how a p-n junction or an energy hill in a semiconducting material are going to be common to all of them. What's going to change is whether or not they can be consistently operated in reverse bias, and what the height of the energy hill is, and basically what the devices are intended to do in a circuit. Okay, so we're going to start with Zener diodes, and that is circuit schematic B here. So the essence of a Zener diode, it is the one and only diode that can be operated consistently in reverse bias without ruining it. It's designed to operate past its reverse breakdown. So it doesn't hurt it unless you go past its maximum reverse limit. It has limits like anything else, but it is literally intended to operate mostly in reverse. You can operate it in forward, and it'll give you a typical forward bias drop, but the important thing is it can operate in reverse bias, and it will give you a very, very, very stable and relatively high voltage drop going in that reverse direction. And because of that, Zeners are used for voltage regulation, because the voltage drop over a Zener is very consistent in a circuit, and it's fairly large. So that's the essence of how it works. So here's one in a circuit, and the reverse bias voltage drop over a Zener is something that comes in the spec sheets, and in fact it's how they're purchased. So you purchase a Zener according to its reverse bias voltage drop. So here in figure 2.23 we have a Zener inserted in reverse bias in a circuit. Here's positive current flow is coming in, and it's opposing the direction of the triangle. We know it's a Zener because we've got the little bent line in front of the diode. And so first question we're going to want to know is what reverse voltage rating Zener are we looking at? We're told it's 5.1 volts. That means to get from this side of the Zener to the other, you drop 5.1 volts. If you're not supplying 5.1 volts with your source, there's not going to be any current flowing. So let's first check, is our source big enough to get past the Zener? Yes. Our source is 9 volts. So if I were to apply Kirchhoff's voltage law, I could start at an arbitrary 0 volt ground. I would go up 9 volts to the upper left hand corner going through my source. I would drop exactly 5.1 volts going through the Zener in reverse bias, and then I would drop my remaining voltage back to ground through whatever current is flowing through the resistor via Ohm's law. So I know what the resistor is, I know what the values are for the Zener reverse bias and my source, so I can rearrange Kirchhoff's voltage law and solve for current through the circuit. In reality, what I would typically use this for would be to use the voltage drop over this Zener as the literal voltage supply for something that I needed to be very stable DC. No ripple like we have with a rectifier, which is something we'll learn about later. This is a very consistent DC. So that's a good way of breaking up the voltage in a circuit as an alternative to just a resistor voltage divider. And as a note, Zeners are one of the semiconductor components that you have available to use in your simulation package with TINA. So you can go ahead and practice using Zeners in a TINA circuit, as well as using them in your proto board with your kit if you are doing a live lab or a physical lab. Typical values for Zeners, 3.6 is one that you'll frequently see. A 9 is something you'll encounter, and they come in a large range of voltages. Okay, a caution about the Zener: if it is in parallel with something else and it is not being provided its breakdown voltage, it won't conduct. So basically it won't be providing voltage control. It will only do so when it's given more than its breakdown voltage, and then it will assume that a voltage drop equal to its breakdown. So, and we'll explore that in some practical circuits. Okay, next flavor of diode is the LED, or light emitting diode, also called a photodiode. So these operate in forward bias. If you put them in reverse bias, they don't conduct and they don't light up because there's no current flowing through. Basically, one of the characteristics these have is that as charge carriers come across the interface, in addition to jumping the energy hill, some of the voltage that you supply does more than just push your charge carriers up or down the energy hill at your interface. Some of that applied voltage that you're putting across the diode is converted to light. And that's one of the reasons these things have such a high forward bias voltage drop, because you're doing more than pushing charge carriers across them. You're siphoning off some of your applied voltage to make light, which is great if you want to make light or create an indicator. So again, we have forward bias voltage, typically much higher than 0.7. Expect somewhere between 1.2 and well over 2, and the higher the frequency of the light that it emits, the higher the voltage drop, because higher frequency light has more energy, so it takes more energy. The brightness of the light, so then the number of photons you're producing per unit time, is going to be a function of the current through the LED. So the color is based on the type of LED you buy. That it's a characteristic of the material that the LED is made of and the nature of the junction, but the brightness is a function of the current that you have flowing through it. And you can look up everything you need to know about LEDs in the manufacturer's specs. So here's an example right here in your textbook of the specs for several different types of LEDs. And we'll hit a few highlights. Typical forward current limits. It's different depending on color for this type of diode, so we can put no more than, let me blow this up so we can see it a little better. A lot of specs are written really small. Forward current in milliamps, 50 milliamps max for red or kind of a yellow LED, 35 max for blue or green. Peak, so you can have a momentary surge of current that's up to 200 or 100 respectively, so really different depending on color. Reverse voltage, total, like don't put more than this amount of voltage in reverse bias. 5 volts, that's not very much. That's much less than some of the switchings. Not a lot of power dissipation compared to the other switching diode we looked at earlier in the chapter. Instead of 500 milliwatts, this is only about 100 to 150. And our forward operational specs, forward voltage drop, and these are cited at a given current: 2.1 for red, 3.4 for blue. So that's a hefty voltage drop. This will not light up unless you provide it with at least 3.5 volts supply. This is a big energy hill in forward bias. And again, the 5 volt reverse is replicated there. And there's some information given about luminous intensity, so how many photons, how bright does the light get for a given benchmark current would be something you would care about maybe if you were using this for illumination or for a signal that had to be seen maybe across the room, because then you could design the circuit around a certain amount of lumens needed to see it. Okay, so big things to bear in mind about LEDs. Operate in forward bias. That forward bias voltage that you apply gets a portion to getting charged carriers across the interface and making light. You will have more current through the device, basically with supply voltage, but you'll have more light depending on current. So your light is proportional to current flowing through. Forward bias voltage differs by the color, and all of your maximums applied forward current and reverse voltage and power dissipation can also vary by color. So that's LEDs in a nutshell. Definitely you're going to want to read your spec sheets when you're deploying an LED, because they vary quite a bit with particular composition, style, and color. So if you're lucky, you'll use a set that are all produced by the same manufacturer, and you can get the characteristics, electrical characteristics by color all in one spec sheet, and then maybe use a variety in your circuit. Okay, so here's an example of an LED being used in a series circuit just the way we had a regular switching diode. So if somebody wants to know probably how much current is flowing, determine circulating current. And that would be important because that's going to determine the brightness of the LED. Maybe we need to know if it's luminous enough at a distance, so we need to know the current because we're going to pick its brightness per unit current off a spec sheet. So we can apply Kirchhoff's voltage law again. So we're going to go from 0 volts at our arbitrary reference at the back end of the battery. We're going to go up the supply voltage, which we're told is 5 volts. And we're going to drop 2.1 volts over the LED because we were told the forward voltage is 2.1. It's probably a red LED. And then we're going to drop the remainder of our voltage in current flowing through the resistor. So we're going to drop a voltage equal to E minus forward bias over the resistor, so we can apply Ohm's law to get current. So we've got 5 volts minus 2.1 volts divided by 330 ohms should give us current. So real simple, but a very different value for that forward bias voltage. Remember, typical silicon switching diodes, rectifying diodes will be 0.7. This is 3 times that much. Again, because some of our forward voltage is making some light for us, as well as just getting electrons and holes up and down the hill. So we can take advantage of the fact that LEDs are only going to conduct in the forward direction to give us an indication of which which direction current is flowing in an AC circuit here. We've got diodes oriented in different directions. So when you have an AC signal, when we've got current flowing, positive current flowing, the forward half of an AC cycle, diode number 1 will be in forward bias and it'll light up. And then when we have the negative half cycle of our sinusoidal waveform, D2 will effectively be forward biased and will light up. So these will blink alternately. Photodiodes. Okay, this is kind of the reverse of an LED, and this is very, very important for people who are looking at use of semiconducting materials for solar cells for power production. So the way a photodiode works is, if you think back about the nature of your depletion zone at a PN junction having a fixed voltage. So we got that charge separation that came from our holes and electrons in our doped materials annihilating one another and kind of creating that effective depletion zone that had a net positive charge on the N side and a net negative on the P side. We have a little fixed voltage source. Well, there's intrinsic semiconducting material in the middle that isn't going to conduct, and effectively it's surrounded by something that's akin to a fixed voltage. So if we were able to create charge carriers in that depletion zone, they'd immediately get zipped away into the circuit by a voltage equal to that energy hill. And basically that's why your reverse saturation current increases with temperature. Well, we can use light the way we use temperature. And so for every photon that literally hits that depletion zone, if we expose it to light, we create a pair of charge carriers, and the fixed voltage associated with that depletion zone zips them away. So the conductivity of that device is dependent on how much light is hitting it, because we're creating charge carriers every time the light hits it. So that's how a photovoltaic device works. We use its fixed charge, and then we use photons to create current that get accelerated by the effective fixed voltage, and then we have power. So that's the essence of how a solar cell works. We can go the other way, and we can actually reverse bias that interface, and then basically to the point where we're not powering a circuit with it, but merely measuring how much photons are available and hit it. So it's a similar mechanism, but a little bit different mode in a circuit. So we would actually be applying a bias to the diode in that sense, and then every time a photon hits, we would get current, but we're not using the fixed charge of the interface to actually create power. But very, very similar. Light goes to current as opposed to an LED, where a portion of our applied voltage goes to light, effectively making light instead of driving charge carriers. Again, very useful for sensors and for power production. Okay, Schottky and varactor. I said there was one diode flavor that didn't actually have a PN junction, two semiconducting materials, and that's a Schottky diode. And it actually has a metal to N-type semiconductor junction. And basically the way that works is the energy bands in the metal conductor, you've got that partially filled valence band, it'll actually bend up or down as you interface that with an N-type semiconductor, and it creates the same kind of voltage hill that we have at a PN junction, really, really similar. So it's going to have a one-way conduction, just the same as we do with our standard PN junction diode, but it operates faster because you got metal on one side. The capacitance is much, much lower, so it can switch quicker. If we reverse quickly the direction of current, like with a square wave imposed periodic signal, it's going to respond faster. It has a lower capacitance, so these are used for very, very fast switching applications. And in case you wondered, we got to metallize the back of every piece of doped semiconducting material that we make a device out of. So if you want to think about it, yes, and I'm sure this would come up if you're kind of extrapolating back, you effectively have a Schottky type junction at the connection points between your wire and any piece of doped semiconductor. And the way it works with a standard diode is the energy hills of those two regions are in opposite directions and cancel out. But if you just had one, you would have a Schottky diode. So you got the symbol for it is this kinky little line above the top, and it otherwise works exactly the same way as standard switching diode, but it's constructed differently, different materials, and lower capacitance, so faster switching, and typically also lower forward bias voltage. So those are the two characteristics. If you need to open the diode, you need a very low energy hill and you need it to respond quickly, that's a good choice. Okay, varactors, and I believe this is the last of our specialty diodes. We mentioned that the depletion zone in any PN junction is basically like the dielectric in a capacitor. And if we apply bigger and bigger reverse bias voltages, we pull charge carriers away from the interface and we widen the depletion zone. So that's like having a thicker and thicker dielectric in a capacitor, and we drop the capacitance. So if we applied a different DC bias voltage across a diode, we could turn it into a capacitor with varying capacitance levels depending on our DC bias. So that gives us what's effectively a continuously variable solid-state capacitor, because we're using the PN junction interface literally as a thickness variable dielectric, and we're using the DC bias voltage to adjust that thickness. So a question might come, so okay, how do we use that? Because we're applying a reverse bias, it's not going to conduct. What use is it? What if we want to put an AC signal across it? If you all took AC circuits, you probably came across the concept of resonance, where we had to have exactly the correct capacitance and inductance combination, and we got this very high or very low impedance in our circuit as a result. Putting one of these variable capacitors, solid-state capacitors, allows us to tune a circuit to achieve resonance. And so we can still pass an AC signal, but we superimpose that AC signal over the DC bias that literally sets the capacitance we need. We might still have a rectifying effect as we try to go backwards on one half of the cycle, but then we can just use two in tandem to overcome that. So these varactors, variable capacitor diodes, are used extensively in oscillators and different types of radio frequency applications where we have to finely tune a circuit with respect to its capacitive inductive characteristics to achieve resonance. So that's a real important aspect of diodes. The PN junction is a capacitor. And it's a nice way to leverage something that is basically inherent to a PN junction. But it's also a good reminder that every time we use a PN junction, we're adding a capacitor to the circuit. And when we look at frequency-dependent applications later on in our studies, that becomes really important when we talk about switching speed and signal processing. Just remember, every time you have a junction, you have a capacitor, and you're having to charge and discharge it. There's a time constant associated with that, and so there's a rate limit to how fast it can change direction. So it's literally the capacitance of your PN junctions that gives rise to all of the performance specs associated with switching speed and time rate performance. So it's not a mystery, it's just the capacitance of the junction. So that concludes our treatment of our diodes in terms of their basic characteristics and the way we model them, and the most typical ones that you might encounter, how to read spec sheets. And for our next chapter and our next module in the class, we're going to jump into particular circuits that leverage the characteristics of diodes, especially for AC signal processing. So hold on tight to those, to mainly that model number 2 of diodes as a switch and a voltage source, and you can use that again and again in some really unique circuits. So stay tuned for next time.